Hi there, I am Seth, and in this video I'm going to explain coefficient alpha, more popularly known as Cronbach's alpha. This is a measure of internal consistency, which is the extent to which items are related to each other, although as we'll see there's a bit more to it when we get into coefficient alpha. Now, internal consistency is kind of like alternate forms reliability, which is where you have different versions of a test and you correlate them with each other to see how related they are. But it's sort of like if we took that idea to the extreme and we like smashed up the test into so many pieces that we were actually looking at how is every individual item related to every other item. So the question is, do these different items all measure the same thing? Now, coefficient alpha is originally based on the concept of the split half reliability, where you would take a test and you'd cut it in half and correlate one half with the other. Really cool idea, but actually not amazing in terms of results because the way you cut it up is going to give you different estimates for reliability. You get a different correlation every single different way that you cut up the test. So Cronbach solved this problem by popularizing what he called coefficient alpha. This wasn't actually his original idea, but even though he insisted we call it coefficient alpha, and he was really embarrassed by what happened instead, we name things after whoever popularizes it, so everybody knows it as Cronbach alpha, but really it's actually coefficient alpha, and that's probably what I'm going to try to call it as much as possible, because that's what he wanted it called. Because he actually didn't invent it. So coefficient alpha is the average of all possible split half reliability. So it sort of takes that problem of, good idea to cut the tests in half and correlate them, but the results change every time. Well, this said, no problem. Let's find what the average would be if we calculated all possible split half reliabilities. Now, I said he didn't create this. That's because this is really just an application of what's called the Spearman-Brown prophecy formula, which had already existed for a while before Cronbach published or popularized this solution to the problem of reliability. So if you've already seen my video on the Spearman-Brown formula, this video is going to be cake for you because you already get the core intuition that underlies this formula. And I hope that when you look at these, you can see it is very much the exact same concept, except some of the variable names are different. Now, I will say, if you are already familiar with coefficient alpha, you've probably seen this hideous formula. People really like this. I don't really know why. I know people like to talk about, like, it's intuitive because of how much of the total variance is covariance. And it's like, okay, but like, what's this correction factor is not very intuitive to look at. I personally don't like this at all. I'm more a fan of this version, which looks just like the Spearman-Brown formula, which to me makes a lot more sense. So that's my view, and that's why we'll stick with this one. So coefficient alpha, alpha is this Greek A-looking symbol. It's an index of internal consistency that's taking into account two things. First, how correlated are the items with each other? Because the more correlated they are with each other, that would suggest they're measuring the same thing, right? But coefficient alpha also takes into account test length, because longer tests tend to be more reliable, assuming that the additional items are all measuring the same construct equally well. If it's not clear why test length would be linked to reliability, go check out the other videos in this psychometrics playlist, especially the one on introduction to reliability and the principle of aggregation. It's called something like that. I don't know. Okay, so that's the idea. It's getting at internal consistency, a form of reliability concerning how consistent are scores across different items in the same test. Now, before I explain this formula to you, I'm actually going to explain a different formula to you, a closely related one that I think is a little bit easier to understand. And it's coefficient alpha standardized. Whenever we standardize it, it makes there be fewer variables to deal with, and I think it's a little more intuitive. So I'll give the core explanation from this, and then I'll convert this to raw alpha in a bit. So alpha standardized. Okay, so it's the exact same thing, but we've swapped out some of the variables. What are these variables? N is the number of test items. And then when you see a bar over a variable in this video, that means average. So this is the average correlation between pairs of items on the test. Okay, now what we're going to do is we're actually going to build this formula from scratch. All right, we're going to start with this basic concept of the average inter-item correlation, and then we're going to build it up into the full version, which is standardized alpha. Sorry, I should have said before, this is the standardized version of this, which means if we were to convert all scores to z-scores, this is what the formula would become. Whereas the normal coefficient alpha is in raw units. They're not standardized. But we'll come back to that, and I'll draw the connection here in a minute. Okay, so we've talked about what the average inter-item correlation is, and I'll just note that we can always express a value as being over 1, because anything divided by 1 is itself. And in this case, it's useful to think about how the average correlation is expressed out of a maximum of 1. So we have however much out of 1. 1 would be the maximum correlation that you could have between items. Correlation can't be larger than 1. Now, we could stop here. The average inter-item correlation is an index of internal consistency. It's just how correlated are the items with each other on average. So that does tell us about how closely they're linked. But coefficient alpha also takes the test length into account. As I said, assuming all items are measuring the construct in the same way to the same degree, then a longer test is going to be more reliable than a shorter test. And so coefficient alpha takes that into account. So whenever I'm talking about the average inter-item correlation, I'm really just, averaging means add things up and divide by the number, at least if you're talking about the arithmetic mean, which is what we are talking about in this video. So we can add up the correlations and divide by the number of them. But to clarify, when I say that, I'm specifically referring to the number of unique correlations. So like if you're looking in a correlation matrix, one thing you may notice is that half of this matrix is a duplicate. So like the correlation between item 1 and item 2 is 0.02. That's also the correlation between item 2 and item 1. It's 0.02 because it's the same thing. 1 and 2 is the same as 2 and 1. So half of this is redundant. We don't want to bring that. We could bring that into this formula, but then we need to change the denominator. So just to keep it nice and easy, when I say the average inter-item correlation, just think about like the lower bottom triangle of a correlation matrix. So there are actually 6 correlations, 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, and 3 with 4. Everything else is a duplicate or a correlation with itself. So these 6 are what we're interested in. We could add up these values and divide by 6, and that would give us the average correlation between items. But what's critical here is that this number, the average inter-item correlation, that's giving us the average amount of consistency for a given item, a single given item. You might be tempted to think that it would represent the average consistency for a given pair of items, right? Because it's like we divided by the number of pairs of items that went into it. But in fact, while that does represent the average correlation between a given pair of items, it only represents the average consistency for a single item. Why is that the case? Let's take a very simple example to think this through. Imagine you're evaluating retest reliability for a 1-item scale. Hopefully you're not using a 1-item scale. I would not encourage that, but just for simplicity, let's say we're doing that. So retest reliability, we're going to have people take the same test at 2 points in time, and then we just correlate the scores. So let's say a sample of people take the test on 2 occasions, a week apart, correlate time 1 scores with time 2 scores. Now think about that. They answered 1 item at time 1, and they also answered 1 item at time 2. That is the correlation between those is only giving you the consistency for 1 item. The fact that there's 2 columns in your correlation matrix doesn't mean we're somehow getting two items here. This is the correlation between two items, but this is actually telling us about the consistency of one item. Okay, so no matter how many items we have in our scale, each correlation between a pair of items is only representing internal consistency for a single item. And that's why coefficient alpha says, whoa, this average inter-item correlation alone, that's not enough information. We have to scale that up, okay? So we start with this, we start with the average amount of consistency for a given item, and then we say, but wait, we don't have a single item, we have n items, however many items we have. So we take that value that we started with, average correlation between items, and we scale it up by the number of items. We simply multiply it times the number of items that we have, which may seem pretty straightforward, but this creates a problem. Specifically, when we do this, we're knocking the average correlation off its typical scale, ranging from -1 to +1. Like, take a quick example. Let's say we've got two items in our test and the correlation is 0.7. If we double that, we come to 1.4. That is not a possible correlation. Correlation's not supposed to be larger than 1. Okay? And if you think of this as 1 being the maximum that this correlation could be. So we're saying, how big is this out of its maximum of 1? When we go here, we could end up with the part being greater than the whole. And that doesn't make sense. The part that makes up the whole can't be larger than the entire whole. It just doesn't make sense. It's like saying you have 10 slices of pizza, and I say, how many did you eat? And you say, I ate 15 of the 10 slices. It doesn't make any sense, okay? So the denominator of the formula simply yanks the result back onto the correct scale. And the way it does this is by saying whatever amount you add up top, we're going to add the exact same amount down low, and that's going to keep it ranging on it with a maximum of 1. So that probably doesn't make any sense. Let's take a quick example to make it make sense. Let's say that we have 3 items, so n is 3. So we take our formula right here, standardized alpha, we're going to replace n with 3. Okay, so we have 3 times the average correlation, then over 1 plus 3 minus 1 times. Okay, now when you simplify this, this bottom part's going to come out to 1. We've got that 1 plus 2 times r. So that you could write that as 1 plus r plus r. Similarly, up top, 3 times the average correlation is the same thing as saying start with the average, then add another one of itself, then add another one of itself. And you can see from how I've color-coded it that I'm just showing you. We started with however much out of 1, then when we increase the numerator by some amount in order to keep it in range, in order to keep the part from being larger than the whole, the denominator says no problem, we're just going to increase the denominator by the same amount. Okay, so that is standardized alpha. Now let's make the jump over to coefficient alpha, which is the same thing, but maybe you would call it raw alpha. It's in unstandardized terms. Okay, so just naming the parts real quick, we're just looking at alpha, and it's equal to the number of items times the average covariance between items over the average variance between items plus n minus 1 times covariance, blah, 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 blah. We'll get into all that in a minute. First thing to notice is this is the exact same formula. They are identical, except the one on the left is standardized, the one on the right is unstandardized. So this is in raw units, the one on the left is in standard deviation units. Specifically, correlation is the standardized version of covariance, as I'll show you. So once we convert to standard deviation, once we standardize the distribution of scores, average covariance becomes average correlation. Similarly, when we standardize the scores, the average variance becomes 1, and I'll show you that in a minute. But let's just work through these one at a time to show how these are really the same, just one is raw, one is standardized. I said that correlation is the standardized version of covariance. I don't want to go too deep down the rabbit hole on explaining what covariance is, but very briefly, this is the formula for it. Anytime we're adding something up and dividing by the number of them, we're averaging. That's sort of what the arithmetic mean is. So what is it that we're averaging? It's a product of 2 deviations. First, we're saying, what's the difference between x and its mean? So on this first variable. Then for the second variable, what's the difference between that person's score and the mean of that variable? So what the gist of this, what this is doing is it's saying, are these things going in the same direction? So if you tend to be high on this variable, do you also tend to be high on this one? If so, the deviation is positive for both, and positive times a positive is positive. Or do you tend to be low on this variable and low on this variable, which again would be a positive correlation because a negative times a negative is a positive. The other possibility is a negative correlation where maybe you're high on this one, so above the mean, but you're low on this other variable, below the mean. That's what a negative correlation is, because a positive times a negative is a negative. So we're taking those cross products of deviations and then we're averaging them. So covariance says, just to put it very briefly, on average, are the scores moving in the same direction for the two variables? Okay, that's what covariance is. I'll make another video at some point giving a visual representation of this, but for now, that's it. So I told you that the correlation is the same concept but standardized, and that's literally the definition of the correlation coefficient. You take your covariance, the extent to which the variables move together, to which they covary, then you put it in standard deviation units. When you have a fraction, you're expressing the numerator in terms of the denominator. So we're saying, what is the covariance expressed in terms of standard deviation units? This is the standard deviation for x. This is the standard deviation for y. And that's literally what the correlation is. It's just the covariance whenever we've got z-scores, or take the covariance and divide by standard deviation. So here is just a summary of what I just said, showing the link between those two things, and just drawing attention to the fact that this average covariance, that's getting at the whole average inter-item correlation concept, but in raw units. Okay, I also told you that the variance becomes 1 whenever we standardize, whenever we convert all scores to z-scores. I keep throwing around that z-score term, so I'm going to explain what that means. Oh, I changed up the notation for you. Sorry, a minute ago I was using x bar to represent the mean. Let me just go back to that real quick. Yeah, so I was using x bar to represent the mean of x. Sorry, here I switched for some reason to using the mean of x. So just imagine that's an x bar, or pretend that x bar is the mean, but this just means the mean, okay? So this is the variance. It's the same concept as the covariance. We're adding up and dividing by the number, so we're averaging, but then we're just multiplying that deviation times itself. So the variance is the average squared deviation. It's literally what it says. Okay, and that's an index of spread. That's telling us how spread out the scores are for this variable. Now, I keep saying z-scores, and I keep saying standard deviation units. So let's talk about how to convert to a z-score. We want to, if we're standardizing, we're going to take that x, that raw score, and then we're going to express it in terms of standard deviation units. So we subtract the mean from it and divide by the standard deviation. Remember how I told you that the numerator is being expressed in terms of the denominator? So a z-score literally says, how far away is this score from the mean, whether above or below? Take that difference and put it into standard deviation units. So how big is this difference in standard deviation units? So I'm now going to insert this into this formula, and I'm going to show you how it comes out to equal 1. If you're really comfortable with algebra, this will be no trouble for you. But if you're not a huge fan of algebra, just don't worry. You can just plug your ears and sing la 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 while I'm covering this, and then I'm going to show you a demonstration in Excel that will probably make you happier than this. But here is a quick little proof of how this works. So I told you I was going to insert this, the z-score, where we've got x, so I did that right here. The mean of x becomes 0 because the mean of z-scores is 0 because we subtracted the mean from every value. You can think that through if you like. So anyway, what's going to happen is this is going to simplify to this expression, 1 over the variance times this. How did I do that? How did I get this out? I just factored it out. Don't stress about this if this doesn't make any sense or if it sounds scary, but for those who know a little bit more about algebra, I'm just saying 1 over, we can factor out this piece, it's squared, this s is squared, we can factor that out. And if we were to multiply this times that, it would go back in. But we're sort of taking it and yanking it out to the side. And so it comes out like this. Now, you might notice we have 1 over s squared, which is the variance, and we're multiplying it times this expression, which is the variance. So anytime that you're taking something like the variance and multiplying it times its own reciprocal, that comes out to 1. Again, if you like algebra, you're probably like, woo, love it, makes sense. But if not, then I'm going to give you a quick demonstration in Excel. And yes, as obsessed with R as I am, Excel really is better for some things. Okay, so let's see. Let's say we've got a variable x. Then I'm just going to make up some random data. Oops. Let's exclude that. And then, boop, 9999. Okay, so let's find the variance of these data, which you can clearly see I just made these up, so there's nothing special about these. Variance of x, this is going to be equal to var.s. This gives us the variance of a sample. Open parentheses, highlight the cells you're interested in, enter, done. So it's this obscene number right here. Okay, now we're going to convert to z-scores. To do that, this is 2 through 13, so I'm going to highlight those cells, and I'm going to say these will be equal to, then spell out standardize. This will convert to, well, for what we're going to do, it's going to convert to z-scores. So we say open parentheses, and you can see it wants the data, then it wants to know the mean, then it wants to know the standard deviation. So it's going to be the data are right here, comma, then it wants the mean that we're referring to. So I'm going to say, well, that's the average, spell out average for the arithmetic mean, and then highlight those cells again, close parentheses, comma. Now it wants the standard deviation. So I'm going to say stdev.s. This is the function for the standard deviation of a sample, open parentheses, highlight those cells again. Okay, then I think I closed all the parentheses. All right, so now these are expressed as z-scores. Only one of them is positive because it's this one that's way, way to the right. Okay, so now whenever we calculate the variance of z, it's going to come to 1. So var.s, variance of a sample, which is right here. Highlight the ones you're looking for. There you go, 1. So you can see there was nothing special about this data set. You watched me randomly hit keys to enter it. And you can see once we convert to z-scores, once we standardize, expressing each of these in terms of standard deviation units, the variance becomes 1. So even if the formula didn't make sense, hopefully you can see how this is just always going to be the case. So there you go. Then, you know what? Fuck it. I'm going to show you how to do this in R as well. Okay, quick demonstration of the same concept in R. Specifically, I'm working in R Studio. Okay, so let's see. We're going to create a vector. Let's say we're going to create a vector of scores. I'm just going to randomly hit keys to create this distribution. Whoops, let's remove that M. Okay, so we've got this set of scores. The variance of this set of scores is this obscene number, and then the variance, if we convert to z-scores using the scale function, is 1. Oh, you know what? So I said Excel was going to be better for this, but this was just so much faster. Okay, so what just happened? I created a vector of these values. I told it to give me the variance, which is this large number, and then you can see scale, when you use the scale function, that converts whatever you've got in there to z-scores, unless you change any of the arguments in there. If you just leave it like it is, it converts to z-scores, and you can see the variance of those z-scores is 1. Yeah, R is just amazing. I love it. Shield your eyes. I'm about to go from a dark screen to a bright screen. Okay, what's left? Oh, okay. Yeah, so I was just showing you how the covariance is analogous to the correlation, except it's in raw units. In the same way, if we were to convert to z-scores, if we were to standardize, this average variance would become 1 because the variance of every single item would become 1. Okay? Okay, so just saying a little bit more about what the variance is, that's telling us how spread out the scores are. So the average variance is how spread out scores are on average across all items in the measure. You can think of it like this. Think of the variance as being like how an item moves alone. So how scores move. So like differences between scores and their mean, the mean of the distribution. Then if you're going with that concept of variance, how an item moves alone, covariance is how scores on two items move together. That's why it's called covariance. It's how two items, well, really scores on two items move together, how they co-vary. So very closely related concepts. So here's the key to understanding this formula. In the same way that the maximum possible correlation was 1, the maximum possible covariance is the variance, right? So this is the average variance. The maximum possible average covariance is V. It's that average variance. So think of it like this. Think of it like the variance is spread in the distribution. And we're saying out of all that variance, how much of it is covariance? This could range from 0, like if the items aren't linked to each other at all, like there's 0 correlation between items. So it'd be 0 over the average variance, so that's going to come out to 0. At the other extreme, it could be, what if it's all of it? What if all of the variance is covariance? If so, then C is equal to V, so this comes to 1. So this should range from 0 to 1 if it's calculated correctly and if the assumptions are correct. All right, so that's our starting place. And all we've really got here is just the concept of the inter-item correlation just in raw units, right? That's all we've really got right now. So then we scale it up by the number of items, just like before. We say here's the consistency for a given item, but we have n items, so we multiply it times n, and then we use the denominator to yank that result back so that the numerator will not exceed the denominator, so that the part will not be larger than the whole. Okay, so hopefully that's making good sense. To put it very briefly and succinctly, the numerator scales the average covariance to the number of items, then the denominator pulls that back onto a 0 to 1 scale. Okay, so in summary, coefficient alpha is an estimate of reliability taking into account two things. First, how intercorrelated are the items, where if they're more intercorrelated, the test is going to be more reliable. And also, two, how long is the test, where we understand that longer tests tend to be more reliable, at least assuming that the additional items are all measuring the same construct equally well. Okay, last thing, let's calculate these things in R and RStudio. Okay, let's see, what are we doing? Okay, so let's use SAQ data. The SAQ is this scale that Andy Field made up. It's a humorous scale called the SPSS Anxiety Questionnaire. It's really a joke more than anything, but sometimes people will use it to demonstrate how factor analysis works and things like that. But let's just go with this data. I'm going to call it SAQ. I'm going to need a couple of libraries first. I want to use the psych package because it's trivially easy to calculate coefficient alpha with psych. And then I also want read Excel because the file that I have is in an Excel spreadsheet, so I want to read it into R. Okay, so I'm going to say SAQ is equal to read underscore Excel, open parentheses, and then let me check where I'm at. I'm currently in my R folder, and I believe it's there. Let's just see what happens. Okay, here we go. So I called it saqdata.xlsx. Cool. So it's in a spreadsheet, and I'm reading it in. Okay, so what this means, I'm assigning it. So from now on, after I run this line, it means when I say SAQ, I mean grab this data set, okay? And then often you'll see me, after I assign something, I'll say semicolon, and then I'll write the thing I assign. What this code says is run everything to the left of that semicolon, then when you're done, show me what you did. This is generally how I write it because I like to see the result. Okay, there you go. Like for example, if I said x is equal to 1 through 3, and I just said go, it's like, okay, cool, sounds good. But it's not actually going to show you. But if you say that and then show me what you did, it's like, sure thing, boss. And then it also gives you the result. Sorry, that's just a little aside. Okay, so we've got our SAQ data. I happen to know that one item needs reverse coded. You don't really need to worry about this, but the third one is not reflective of anxiety. It's like inversely reflective. So it's equal to itself. I'm just reverse coding that item real quick. If what I just did doesn't make sense, you should check out my video on recoding and reverse coding in R, which is somewhere on my channel. Okay, so I just reverse coded that item. Don't worry about it, not a big deal. Okay, so we've got these items and we want to calculate coefficient alpha. This is so easy to do if you've loaded the psych package. By the way, if you haven't used it before, remember to use install.packages and then put it in quotation marks to install it. Once you've got it, you don't have to install it again, but you do need to load it up using the library function anytime you boot up R. Okie doke. So from within psych, we've got this function called alpha now, and you can see all kinds of fun stuff here, but it really just wants the data. And you can, oh, I guess I could have reverse keyed right there. That's okay, doesn't matter. Okay, so we're going to calculate coefficient alpha for the SAQ. And let's just run that and see what happens. Let's see what we get. Ooh, warnings. It thinks some things need to be reversed, but it's wrong because we already did the reverse coding. And you can see all kinds of fun statistics populating. Once you learn more about psychometrics, these will be fun and useful, but for now it probably just looks horrible. Oh, and finally up here we can see raw alpha's 0.81. So this is kind of a lot. If you ever don't want to deal with all that output, we can make it be more specific. So first of all, I'm going to suppress those warnings. So I'm going to say comma warnings equals false. By default, it was invisible, but it has this argument switched to true, which means warn me if it seems like something needed to be reverse coded. I'm flipping that switch and saying, no, turn that off. I don't want your warnings. And specifically, I don't want everything. I only want what's in this top portion, and I only specifically want what's called raw alpha. Okay, so to be more specific about the output we get, I can use $sign at the end, and then I'm going to use total, which is going to be grabbing from this section right here. Then I'm going to say $sign again, so I'm going to say within that, just give me the raw alpha. So I am expecting to get this 0.81 when I run this. Let's see what happens. Okay, so now instead of all that, so in case it's not clear, all that's actually showing up now is that one line of code, then it gives the result. So 0.8058896, that rounds to 0.81, which is what we expected. So very easy to calculate coefficient alpha using the psych package. But you know what? It's not a horrible idea to double check these functions and make sure that they're doing what you think they're doing. So you might wonder, what's his name? William Revell, I think is his name, created the psych package. Did he do it correctly? Let's check and see. So let's build this code ourselves from scratch and just see if we get the same result. Okay, let's see. So what's our formula? The formula is going to be equal to, well, let's just write it here. Let's say it's n times the mean covariance. I'm not going to use C with a bar over it because that's just going to get painful. I don't want to do that. So it's easier to just say mean covariance MC divided by, open parentheses, the mean variance, so MV, mean variance, plus, open parentheses, n minus 1, close parentheses, times the mean covariance. That's just that formula that we've been working with. This is the raw version, not the standardized. By the way, I don't know if you were paying attention, but alpha also gave us the standardized alpha, if you were paying attention. So here's in raw units, here's in standard deviation units. Sorry, I just had to mention that. Okay, anyway, so we're getting raw coefficient alpha. Let's see. So now we need to assign each of these three variables that we've named. So let's see. Let's say n is equal to the length of SAQ. Let's just run this real quick and make sure it's doing what I think. Length, I believe, says how many columns are in there. So the length of this data set is 23 columns. So that's good. So n is equal to that. I like that. Now we need MC, the mean covariance. So we're going to calculate the mean of the covariances of SAQ. Okay, so I'm going to modify this a little bit, but what this is saying is from now on, MC means calculate the mean of the covariances of this data set. But right now, it's going to calculate that for all of the pairs of items, including duplicates and things like that. I only want the lower triangle. Remember how I had that visual earlier where I drew the triangle around certain values and I said I only want that lower triangle? I'm going to make R only look at those. So I'm going to say out of the covariances bracket, open bracket, only give me the lower dot triangle for covariances of SAQ. So this says give me the mean covariances in this data set, but only from the lower triangle here. Okay, there might be a more efficient way to write this, but I don't know how, or I can't think of it right now. Okay, so we got MC. Run it. Okay, that it didn't get an error, so that's good. Okay, so now we'll say the mean variance is equal to the mean of, let's use the sapply function. This is going to apply the same function repeatedly. So it says, give me some data, then give me a function, and I'll do it repeatedly. So the data is SAQ, comma. The function is VAR for variance. So this says the mean variance is the mean of the variance of each column. So that should work, MV. Okay. So it didn't give us an error. So now we've assigned N, MC, and MV, and let's just run our code real quick. Let's see, what were we expecting to get? We were expecting to get 0.8058896, and let's see what we do get. 0.8058896. So that works. Looks like Will did this correctly. Can I call you Will? I'm going to call you Will. Now, you might look at this and think, wow, that's kind of a lot of work, all these steps. And that's right. In actuality, you would probably just use the alpha function or whatever package you like to use. I like the psych package. But this is this is useful for just working through and making sure that you really understand what's going on at an algorithmic level, which is what I always recommend. So there you go. That's how to calculate coefficient alpha in R. Now I'm about to go from this dark screen to a bright screen, so shield your eyes. Okay, anyone watching like at night in the dark just had their retinas burned. Okay, so there you go. That is it for coefficient alpha. If you have questions, comments, thoughts, or concerns, shoot me an email, or if you have any video requests, topics you want to see that are within the realm of stats, psychometrics, things like that, let me know. Otherwise, that's it. Have fun.